fibrous capsule around it, and 20 to 25% of cardiac output at rest is going through this renal artery. So this little organ receives 20 to 25% of cardiac output. And as it comes in here, it fills up the organ and it kind of billows. It creates this space, which is the renal sinus. And within that sinus, there's an indentation. This area is the hilum of the kidneys. It's where blood goes in and out and the ureter comes out of. The first artery is the renal artery. It splits into two segmental arteries. The segmental arteries travel through the medulla. This part's the medulla, this part's the cortex. The medulla is made up of pyramids, and in between them is columns. The blood goes between the pyramids, travels up the columns as an interlobar artery. So if I point to this artery, it's interlobar. Then it arcs over the pyramid. They look like triangles here, but in 3 dimensions, they're like pyramids. They're a cone. They point down to the bottom. So it arcs over the pyramids as an arcuate artery. And then it sends tributaries up through the cortex, known as cortical radiant arteries. Renal artery, segmental artery, interlobar, arcuate, and then cortical radiant into the cortex. Within the cortex is where you have your nephrons. They're the functional unit of the kidneys. There's 1 million nephrons in each kidney. So if this is a cortical radiant artery, there will be a branch coming off going into the nephron. And the first portion of the nephron is called the renal corpuscle, sometimes called the glomerulus. You can use that interchangeably. But I think it's better defined as a renal corpuscle. And so these little dots here are renal corpuscles. The portion of the nephron where plasma is filtered is within the renal corpuscle. So here is the cortical radiant artery, here is the arcuate artery, gives off a cortical radiant branch, and an afferent arteriole comes off of there, goes into the renal corpuscle. The renal corpuscle consists of a glomerular capillary bed that's drained by another arteriole. This would be the efferent arteriole.
Which one?
So the afferent comes in,
okay.
And the efferent leaves. And you can tell that this is leaving it because this one is coming off the cortical radiant. So that's going to be the afferent. It creates hydrostatic pressure within the glomerulus by draining it with another arteriole. And we can control that pressure by dilating this vessel and constricting this one. We increase glomerular pressure. If we need to do the reverse, we can constrict this one and relax that one. We would decrease glomerular hydrostatic pressure. But that hydrostatic pressure, just like increasing the knob on a hose, would cause more of the plasma to come out of the capillary and go into this corpuscle where it's caught by Bowman's capsule. This purple thing here is Bowman's capsule. It's like a catcher's mitt for any filtrate that comes out of the glomerulus. And there's opposing pressures, because eventually we build up hydrostatic pressure in Bowman's capsule. That's going to resist plasma coming out. Plus, no proteins come out of that glomerulus. So there's osmotic pressure that will tend to try to suck water and filtrate back into the capillary. But fortunately, the hydrostatic pressure of the glomerulus overcomes that. And there's a filtration rate of about 125 mLs per minute, where it leaves into Bowman's capsule and then continues down into the renal tubules. That's the second part of the nephron, the renal tubules. It's shown here in pale green and then in dark green. Filtration takes place in the corpuscles. Once filtrate goes into the tubules, it's destined to go out the body. It's outside of the body. We took it out of the bloodstream. So we have to reabsorb nutrients. The function of reabsorption occurs within this renal tubules, and it will reabsorb about 99% of the filtrate. We can't lose 125 mLs per minute, or within the course of a day, we wouldn't have anything left. So all but 1% of the filtrate is reabsorbed. And then there are some substances that never made it into the filtrate that we want to make sure we get rid of. They wind up being secreted into the tubules. So the tubules serve to either reabsorb needed nutrients or secrete metabolic wastes that didn't make it into the filtrate. In the end, everything that leaves the tubules goes into the collecting ducts, and from the collecting ducts they'll go out as urine if they're not further reabsorbed or secreted. The first part of the tubules is proximal convoluted tubules. About 100% of our nutrients, our amino acids, free fatty acids, and glucose are all reabsorbed there, and 2/3 of the water is already reabsorbed. Doesn't make a difference if ADH is there or not. We reabsorb it. It's known as obligatory reabsorption. So you might have another 35% of the filtrate left at this time, and they go down into this loop of Henle. There's a descending loop, which you see becomes very thin down here on the descending side. There are aquapores in there that will allow more water. About half the water that enters there is now reabsorbed at this point. If we had, I don't know, 35% of the water, by the time it gets out of here, it's 80%. The reason why water comes out is because the deeper we get, and in this case they're showing this loop of Henle is going into the medulla. The medulla is the saltiest of all the meat in our body. Has a lot of sodium, even has some urea. So it's so highly concentrated in salts that if you give water the opportunity, it's going to leak right out of there. Osmotic pressure. This filtrate has the highest osmotic pressure when it gets to the base of the loop of Henle. Because so much water has leaked out, the filtrate is now maximally concentrated. And that helps it on the ascending side, because as we go up this ascending side, the walls here become thicker because they're loaded with salt pumps. They're pumping out sodium and potassium at rapid rates. Chlorine is following, and all kinds of minerals are coming out. So the ascending loop of Henle, the thick loop of Henle, is pumping out sodium and minerals. The fact that water comes out on the descending side makes it more concentrated, and that enables these pumps to kick out the salts. The more salts that are pumped out on this ascending side helps the descending side get rid of water, because it adds to the osmotic pressure of that interstitial area. So it's known as a countercurrent of multiplication, because countercurrent, one's going down, one's going up, that's countercurrent. multiplication, the fact that water is coming out of here is assisted by the opposite side, flowing in the opposite direction, and the fact that water comes out assists that opposite side for pumping out salts. So one side gets rid of water, one side gets rid of salts, they both help each other. They act synergistically. So it's known as a countercurrent of multiplication. And now maybe you have 20 or 15% of the filtrate left. You go into the distal convoluted ducts, tubules, distal convoluted tubules. Here we're going to absorb some more of the filtrate, and we also secrete things into the filtrate here, like penicillin, drug metabolites, creatinine, which maybe didn't make it in. A lot of creatinine is filtered over here, but not all. We only filter about 20% of the plasma goes out in filtrate. So there still is creatinine that leaves in the efferent arterioles, and it's a waste product, and it's secreted into this distal convoluted tubules to make sure we get rid of it. Creatinine is not reabsorbed at all, but it is secreted in. And then towards the end of the distal convoluted tubules and throughout the collecting ducts, we're going to do fine tuning. If we need to reabsorb more water, that will only occur if ADH is present. If we need to reabsorb more sodium, that will only occur if aldosterone is present. And aldosterone will also help us reabsorb more water, because wherever salt goes, water follows. So if we need to help raise our blood pressure a little bit, aldosterone is released. It affects these principal cells, especially seen in the collecting ducts and in the later half of the distal convoluted tubules. And if we need to take in more fluids as well, the principal cells respond to ADH, antidiuretic hormone. So that last 10% or so of water is either going to go out as urine if ADH is not present, or we're going to reabsorb it. If you didn't drink it all during the day, you reabsorb it, and then you have less urine, and the urine you have is much more concentrated. So this is known as obligatory reabsorption. Facultative, Obligatory occurred in the proximal convoluted tubules and the loop of Henle. But over here, it's facultative. It will not occur unless ADH is present. So the principal cells don't usually have aquaporins or sodium-potassium pumps. But if ADH is there, they put in aquaporins. If aldosterone is there, they start putting in sodium-potassium pumps. And now the filtrate continues down here. There's these cells called intercalated cells. Again, I'm not asking you this for lab. Maybe it will be on lecture. I'm not sure. I don't get even that picky, other than understanding that facultative water reabsorption occurs there because of ADH, and sodium reabsorption occurs there only because of aldosterone, even if you don't remember what the cells were called. But in the intercalated cells, they look at pH. And if your pH of your plasma is getting too low, there's too much acid, they'll start secreting hydrogen ions into here and reabsorb bicarbonates into the bloodstream to help buffer your blood, to keep the pH close to 7.4. So the fine-tuning in terms of blood volume, osmolarity, and pH is all performed within these collecting ducts. And they go out the bottom here as a papillary duct. And once it leaves the papillary duct, the papillary ducts are all down here. This is a papillary duct. They go into minor calyx or minor calyces. Here's a minor calyx, here's a minor calyx, here's a minor calyx. This is a major calyx because there's like 3 of them and maybe 4. One from underneath is probably coming in there. But there's at least 3 of them all going into this area here. Here's a minor calyx, here's a minor calyx down, here's another one. This area here is a major calyx. The different major calyces all dump into this area that's known as the renal pelvis. So from the renal pelvis that's over here, it comes into the ureter. Blood winds up coming into the kidneys, getting filtered in the nephron at the renal corpuscles, either reabsorbed or things are secreted into it through the renal tubules, down the collecting ducts. What's reabsorbed and what was never filtered winds up leaving out the renal vein. Again, with vein, I'm not going to point out veins, but you're going to have an arcuate, you're going to have a cortical radiant vein, an arcuate vein, interlobar vein, and then you leave the renal vein. So the renal vein, which is deoxygenated now, has been filtered. So it's the proper pH, volume, sodium osmolality is there, just the way the body wants it. And the rest of the stuff, it removed the urea, the creatinine, the uric acid, all of those nitrogenous wastes. The rest of that stuff goes out the ureter as urine. So it's got one of 2 fates. It's either going to be returned to the body or it's leaving as urine. And this thing also shows this model, and there's 2 of them like that, so I'll use both of them on the test. Bless you. The model shows an afferent arteriole coming in. This is Bowman's capsule. Here's the afferent arteriole, and it forms the glomerular capillary bed, and it leaves as an efferent arteriole. They're trying to show you this little white spots here is the fact that Bowman's capsule has a parietal layer on the outside and a visceral layer on the inside, and that visceral layer has pseudopods that make slits, and they also act to filter the capillary, not to let large substances out. The capillaries are fenestrated with holes, they have a basement membrane, and then they have these podocytes that all are designed to filter so that only small things can get through there. And from Bowman's capsule, you go to proximal convoluted tubules. This thing also shows the distal convoluted tubules coming out here, and there is a thickening of cells here, known as the macula densa. I'm not going to ask you that for lab, but probably should know that for lecture. This is the afferent arteriole that has a thickening of cells, just near the glomerulus. These are juxtaglomerular cells. So macula densa cells of the distal convoluted tubules and juxtaglomerular cells make up what's called the juxtaglomerular apparatus. So this is the JGA, juxtaglomerular. Here's the glomerulus, it's right next to it. Juxta is next to. Juxtaglomerular apparatus. For the purposes of lab, that helps us control the pressure going into the glomerulus so that it regulates glomerular filtration rate. We always want to keep it constant, close to 125 mLs per minute. So if blood pressure gets too high, it causes these cells to tighten up, and these to loosen. If blood pressure gets too low, this will dilate and this will constrict. It's largely regulated by these JGA cells. And renin is released from JGA cells if the blood pressure systemically drops too low. One other thing to point out from here, when the efferent arteriole leaves, it then surrounds the tubules. These are peritubular capillaries. And they also surround the loop of Henle, where you might call them vasa recta. If you see capillaries in the medulla, the pyramids, we call them vasa recta capillaries. They're similar to peritubular capillaries, but they're found in the medulla, so they gave them a different name. And that takes care of this model. With this one, I guess from here, you can see that, or can you see? Maybe you can see it. Yeah, I don't know. It's supposed to be that on the right side, the pole of this kidney is a little bit lower than this one's a little higher on the left, because the liver is over here. So the kidney is a little lower on the right side because of the liver. They're showing you a nephron up here, but I won't use